This is a follow-up on the handout that I sent out via email yesterday. I gave you some examples of transforming integrals with an idea that's similar to U substitution but sort of backwards. And I wanted to follow up on that idea a little bit. I mentioned that the hard part of doing that sort of substitution is knowing what is a good idea, or what substitution is a good idea. And I want to look at today a couple examples of integrals that sort of give us a hint on what is a good, or how to choose a good substitution. So this is an example from the handout, actually. It's the integral from 0 to 1 of x squared over the square root of 1 minus x squared. And this 1 minus x squared part, this is going to be key, because this looks kind of like a rearrangement of one of the Pythagorean trig identities. So you might remember that 1 minus sine squared theta is equal to cosine squared theta. So what this is telling us is if we choose as our substitution x equals sine theta, then the inside of this square root is going to turn into cosine squared, and that means we can do the square root, and that should simplify everything. So that's the idea that gives us, or that's the feature of this integrand that gives us this idea, x equals sine theta, for a substitution. Of course, once we've chosen x equals sine theta, we have to get rid of all of the x's in this integral and turn them all into thetas. And that includes the x right there in the differential, so we need to calculate dx. So dx is cosine theta d theta. All right, and now we can transform this integral. So it's going to become the integral of x squared, well, x is sine, so x squared is sine squared theta over square root 1 minus x squared, but that's sine squared theta, times dx, and dx is cosine theta d theta. Okay, so it looks like we've made a mess, but actually this is going to be not too bad. Let's think about the bounds, though. This bottom bound is 0, and that's an x value. And looking at our substitution equation right here, x equals sine theta, when x is 0, so x is sine theta, when x is 0, what does theta have to be? Well, what angle makes sine equal to 0? It's 0, so the bottom bound in theta is 0. All right, and now for the top bound, when x is 1, what's theta? So what angle makes sine equal to 1? It's pi over 2. So the top bound is now pi over 2. Okay. Now we should simplify this equation, or this expression. So integral from 0 to pi over 2 of sine squared theta over, now the stuff inside the square root, this 1 minus sine squared theta, this is cosine squared theta by that Pythagorean identity, and the square root of cosine squared theta is, well, you want to say it's just cosine theta. Actually, it's the absolute value of cosine theta. But on this interval from 0 to pi over 2, cosine is positive, and so we don't need to write down the absolute value. We can just write cosine theta. Okay, and then the cosine theta d theta from before. And a miracle happens. The cosines cancel. It's almost like someone arranged for this to happen ahead of time. And so our integral is now the integral from 0 to pi over 2 of sine squared theta d theta. All right, well, you know, integral of sine squared, that is the sort of integral that we worked on in the section on trigonometric identities. So hopefully you remember that the way to handle sine squared is to use the double angle identity. Sine squared is 1/2 1 minus cosine 2 theta. Like so, d theta. And now we can integrate this piece by piece. Let's pull out the 1/2. Integral of 1 with respect to theta is theta, okay, minus, and then integral of cosine 2 theta. You might need to do a little substitution to keep track of the constant, but you end up with 1/2 times sine 2 theta. And we need to evaluate this at 0 and pi over 2. Now just a quick check, if we differentiate theta, we get 1. If we differentiate 1/2 sine 2 theta, we do get cosine 2 theta, so this is the correct antiderivative. Okay, so 1/2 times. Now fortunately, when we plug 0 into this for theta, we get nothing but zeros, so let's just plug in pi over 2. We get pi over 2 minus 1/2 sine of 2 times pi over 2, but that's pi. And so this part with the sine of pi, that's just 0. So this whole thing becomes 1/2 times pi over 2, so that's pi over 4. And that's it. There are a couple other situations where the integrand gives us a hint for what is the appropriate substitution to make, and we'll look at another example of that in a minute.